Welcome to the last part of this lecture. We're going to talk about engineering strain, cubical dilation, rotation, and a stretch. Engineering normal strain is basically diagonal elements of infinitesimal strain tensor, epsilon. Let's assume n to be a unit vector in the direction of dx. D capital X. So we can define Nj as D capital Xj divided by the length of the D capital X. Here you see it, and you see it is in the direction of D capital X, the reference configuration. For infinitesimal deformation, we divide the change in the length relation that we've seen in the previous part of this lecture by a square of the length of D capital X. This is what we get. So dx squared minus D capital X squared divided by a square of length of D capital X equal to the other side of the relation divided by the same thing. If we expand this term, we end up with length of dx minus length of D capital X divided by D capital X, and the summation of the length is divided by the length of D capital X. Since length of dx and length of D capital X, basically the length in both the reference and current configuration are almost equal, this part becomes almost equal to 2. On the other hand, D capital Xk divided by the length of dx is basically the kth element of n, the normal vector, the normal unit vector along D capital X. The same for D capital XL divided by the length of D capital X, that's the lth element of n, this normal unit vector, this unit vector. So basically, engineering normal or longitudinal strain that we show by epsilon of n can be defined as change in length per unit of initial length in the direction of initial length, which is defined by D capital X or unit vector n. And we can write it as length of dx minus length of D capital X divided by length of D capital X is equal to epsilon KL and K and L, or basically normal vector dot epsilon infinitesimal strain tensor dot n normal vector, and it gives us the engineering longitudinal strain along n. Look at here how we define different terms here. Okay, let's assume n is in the direction of x1, then n is capital I1. So epsilon of n is now epsilon of I1, which becomes I1 dot epsilon dot I1. That gives us epsilon 1, 1. Basically first row, first column element of epsilon. The same can be done if we assume n is I2 or n is I3, basically along x2 or x3. So we can say the diagonal elements of epsilon, the infinitesimal strain tensor, are normal strains, epsilon of I, in initial reference coordinate directions, capital I. Just note the difference between length of dx minus length of D capital X, which you see here in blue, with the vector dx minus the vector D capital X, which is this vector. So just note the differences. Okay, What about the off-diagonal elements of epsilon? We call that engineering shear strain. Here assume we have again infinitesimal deformation but of type shear. So we have a change in the right angle of this cubic element. We define engineering shear strain as gamma equal to P divided by 2 minus theta. The small change in the angle theta between dx1 and dx2 vectors, which are two initially right angle vectors dx1 and dx2. Note that this is dx, the length of the edges of the original cube are d capital X, and the director of the deformed cube are dx. And basically you can define the off-diagonal elements as the change in this right angle, initially right angle theta, and define that as basically half of the engineering shear strain. Okay, let's drive that. We write dx of 1 dot dx of 2. We already know that it's length of dx of 1, length of dx of 2 multiplied by cosine of theta. But on the other hand, writing dx as a function of d capital X, we find we can write it as d capital X of 1 dot d capital X of 2, which these two are orthogonal, so the result of this dot product is 0, plus d capital X of 1 dot 2 epsilon dot d capital X of 2. So basically we can say that cosine of theta is equal to bringing these two terms to the other side, d capital X of 1 divided by length of dx of 1. This is basically the definition of a normal, a unit vector along the first principal director, principal director multiplied by 2 epsilon multiplied by d capital X of 2 divided by dx of 2, which is basically a unit vector along the second principal director. And also cosine of theta is equal to cosine of half of p minus gamma, which is almost equal to sine of gamma, and which is almost equal to gamma because we're talking infinitesimal strain anyway. So we can write the whole thing as gamma is approximately equal to n of 1 dot 2 epsilon dot n of 2, and n of 1 and n of 2 are unit vectors along the first and second reference frame unit vectors. Now let's substitute n of 1 with I1 and n of 2 with I2 as we've done before. Replacing it in this equation, we end up with gamma 1, 2 is equal to twice of epsilon 1, 2. Basically, putting together what we've learned here and in the previous slide, we can say that gamma ij is twice epsilon ij when I and j are not equal, and also epsilon, the infinitesimal strain tensor, is equal to this relation. The diagonal elements are the engineering normal strains, and the off-diagonal elements are half of the engineering shear strains. In general, we can say epsilon off-diagonal elements of the engineering shear strain, gamma representing the change in the initial right angle theta between the coordinate axes I and the undeformed configuration, as you can see in this figure. We can define something called cubical dilation or volume change ratio for infinitesimal case. In this case, again, assume a cubic element with edges d capital Xi. So basically, we can write dxi equal to 1 plus epsilon of I multiplied by d capital Xi. That's how we find the deformed cube edge lengths as a function of the undeformed cube case. Now let's define the change in the volume ratio. We already know that the change in the volume is dx1, dx2, dx3 minus d capital X1, d capital X2, d capital X3 divided by the initial volume, which is d capital X1, d capital X2, d capital X3. Replacing for dx1, 2, and 3, we get this. And then neglecting higher order terms after basically doing the multiplication here, and cancelling d capital X1, d capital X2, d capital X3, we get delta V over V is approximately equal to epsilon 1 plus epsilon 2 plus epsilon 3, or basically epsilon II, which is the first strain invariant of the infinitesimal strain tensor. So the summation of the diagonal elements of the infinitesimal strain tensor gives us the volume change ratio in the infinitesimal deformation case. Here is an example. It says for the deformation field given by the equation here, x as a function of capital X, where k is a small constant, determine the engineering normal and shear strains, and also volume change ratio delta V over V. So we have infinitesimal strain case. So we know that 2 epsilon ij is equal to ui comma j plus uj comma I, and u is the displacement map, basically x as a function of capital X minus capital X. So just forming the displacement map u, and then using this relation, we can find twice epsilon is equal to 0, 2k minus 2x1k 0, 2x2k minus 2x1k 0, 0, 0, 0, and 0. Now you see all of the diagonal elements are 0. So these are basically the engineering normal strains. And the off-diagonal elements for gamma 1, 2 and gamma 2, 1, it's basically twice epsilon 1, 2, which is equal to the term that we found here. That's the engineering shear strain in the direction of 1, 2, but for the direction of 1, 3 and 2, 3, this is 0. For the volume change, we already know that it's equal to the first invariant of this matrix, and that is 0. So as a result of this deformation, we get no volume change. Okay, we can do a decomposition for for any deformation gradient tensor and get an infinitesimal deformation and a rotation tensor out of it. Let's see how it's being done. Assume a general displacement field. You see it here, the final state and the initial state. Let's form the general displacement u in terms of infinitesimal deformation or a strain tensor epsilon, which is a symmetric tensor. You see it here. And an infinitesimal rigid body rotation tensor omega, which is asymmetric, or which is skew symmetric. You see it here. So in the rigid body rotation case, there is no change in the shape or the size. It's just rigid body rotation. There's no strain. But in the pure strain case, we have the change in the size and shape, but there is no displacement or rotation. Let's see how to work it out. We can basically write du as, we already know that it's ui comma j d capital X j, but let's write it this way: half of ui comma j plus uj comma I plus half of ui comma j minus uj comma I. We name this part, which gives us a symmetric matrix, as epsilon ij, and this right part, which gives us a skew-symmetric part, as omega ij. So if basically d ui, which is the gradient of u, becomes this format, the symmetric part of gradient of u, which is the strain, takes this shape. So see that the diagonal elements remain unchanged, but the off-diagonal elements, we have half of ui comma j plus uj comma I, and it is symmetric. And for the skew-symmetric part of gradient of u, which is the rigid rotation part, you see that the diagonal elements are 0 now. The off-diagonal elements are equal but with opposite sign, and they're equal to half of ui comma j minus uj comma I. Decomposing a general displacement gives us the strain part of that general displacement and the rigid rotation part of that. We can define a quantity named a stretch ratio, shown by lambda. It's the amount of a stretch along the unit vector n, which we define as dx divided by the length of dx. You see n defined along dx in the reference frame here. Lambda along n is defined as dx divided by the capital X. So the length of dx divided by the length of the capital X. You see dx here, you see the capital X here, and it basically gives us the change in the length along n. If n is along one of the reference axes, we can show that lambda of I square is equal to 1 plus 2 times E11. So basically, and if j is equal to 1, obviously. So the stretch ratio along one of the reference frame axes can be found from this relation. We can also define a stretch ratio lambda in the current or deformed configuration in the direction of n, which is basically dx over length of dx in the current form reference. You see it here, n is along dx, and this time we define 1 over lambda along n as length of d capital X divided by length of dx. So note that this is basically length of d capital X divided by length of dx, but defined along n. You see that n and capital N are not aligned. So the relation for gamma, for lambda and capital lambda may give us different values. Also, if n is one of the current frame directors, we can show that 1 over a square of lambda along that director is equal to 1 plus 2 E11 in case j is 1, obviously. For similarly, we have it for the case that j is 2 or 3. And as said, capital lambda along capital N is not necessarily equal to lambda along N. But note that lambda and capital lambda are scalar values. Here is an example. We have a deformation field, x as a function of capital X, k is close to 1. So basically, the relation of x1 with capital X2 and 3 becomes almost 0. So it's a small deformation. It says determine the infinitesimal symmetric and skew symmetric tensors based on the deformation field, and also a stretch ratio along the reference and current frame axis for infinitesimal case, where k is almost equal to 1. And also as an activity example, find the stretches lambda and capital lambda for finite stretch case. Basically for arbitrary values of k. Okay, so let's first find u as x minus capital X, the displacement field. Then we know that u is almost equal to capital U because k is very close to 1, infinitesimal deformation case. So for du, we use basically gradient of a capital U, which gives us this matrix. The symmetric part is easily keeping the diagonal elements. For off diagonal elements, it's half of duij plus duji. This is the result. And the symmetric part, as you know, is the strain or deformation. The skew symmetric part, the diagonal elements are 0, and the off diagonal elements are skew symmetric. So it's half of duij minus duji. And as you see, we get similar off diagonal elements but with negative values. This is the rigid rotation part of that deformation.